I will explain you theorem 6.1 in this video. So here you can see the statement if G is bipartite, that is they are given you a graph and the name of the graph is G and this graph is bipartite graph. Is that clear? If that's so, then what we have to prove is we have to prove then chi dash equal to delta. That is what we have to prove. So when I read this statement, you have to know what is called chi dash. Chi dash means H chromatic number is denoted as chi dash. If chi dash of G means H chromatic number of the graph G. That is what the meaning. Now here rise a question. What is called H chromatic number? Okay. I will tell you what is called H chromatic number. If there is a graph, look at this graph. Okay. If there is a graph, imagine, okay, not to let you understand the concept, I'm telling you what is called H chromatic number. H chromatic number means you are coloring a graph, coloring the edges of the given graph. Okay, the minimum color, if imagine if a graph is having 6 edges, then you can color it with 6 different colors. Here, H chromatic number means you have to use minimum number of colors to color all the edges of that graph. Okay, if I'm coloring a graph having, if imagine a graph is having 10 edges, I'm coloring that graph with 2 colors. Okay, minimum number of colors I have used, right? So this 2 is the edge chromatic number of that graph having 10 edges. Is that clear? So here, I hope now you are clear with what is called chi dash. Now let us move on to delta. Delta means, imagine a graph. In the graph, you can see so many vertices. So here delta means maximum degree of the graph G. Okay, is denoted like this. So chi dash is what? H chromatic number and delta means maximum degree of the graph. Okay, so if G is bipartite, then you have to prove this. The H chromatic number will be equal to the maximum degree. That is maximum degree of the graph and the minimum color you are using, both will be equal if G is a bipartite graph. Or if G is a bipartite graph, this condition will be satisfied. This is what you are going to prove now. Is the statement is clear now? I will explain you the proof of this theorem now. Here you can see the proof. Let us follow my notes so that it helps you to feel easy when you look at the proof of this theorem. Okay, so that is why we can follow my notes. So here first what you have to do is, in the proof you have to write a given. The statement they are given you what? G is a bipartite graph, right? So that is what you are writing here. The first line of the proof. Given G is a bipartite graph. Is that clear? Now we have to prove this, right? So you are in the next line you will write to prove this. And after that you are saying suppose this not equal to delta means, then if they are not equal means you are taking chi dash great, you are taking, okay, you are taking a graph and the graph is bipartite graph. Okay, note that point. You are taking a graph and the graph is having chi dash greater than delta. That is how you are taking. Okay, at the end you will bring the contradiction. Okay, suppose you have to prove equal to, but you are taking not equal to. So at the end of the proof, what you will do? You will bring the contradiction, right? So that kind of proof we are going to write now. So I hope you understood till now. Till this. Okay. Now what you are doing is you are considering a coloring. Okay, that is script C. Script C denotes the coloring. Okay. How you are coloring? Here you are having too many edges. Edge 1, edge 2, edge 3, edge 4. You are coloring each edge with different colors. You are coloring, okay? You are coloring this edge with one color and this with another one color. And you are using delta colors. You are having delta number of edges and you are coloring it with delta colors. Is that clear? Or I can say if there is a 5 edges means you are coloring it with 5 colors. That is what you are taking. Now that okay using what I have said, now you are going to write that in the form of sentence. So here let script is equal to this. Be an optimal delta edge coloring of G. What is mean by delta edge coloring? I told you they are coloring it with delta colors, so you can say delta edge coloring. Okay, so what is called optimal delta edge coloring? Optimal delta edge coloring means if there is a graph having 5 edges, then you can color that graph with at most 5 colors. You can't use more than 5 colors, right? So that you can say that 5 edge coloring as an optimal coloring of that graph, okay, of that graph. Imagine if a graph is having, look at this graph. This graph is having how many edges? 4 edges, right? So you will color this with 4 colors. You can't use more than 4 colors because you are having only 4 edges. So maximum color you can use to color this graph is how much? 4 colors. So that you can say this is optimal edge coloring, you can say. Okay, now you can't use more than this 4. Okay, so you can say that is an optimal coloring. Similarly, here you are having delta, you are using delta colors to delta number of edges. So that you are writing this coloring be an optimal delta edge coloring of G. Can you understand that? I explained too much. I believe that you did not get confused. Okay, now you are taking a vertex u, okay? You are from the graph, that is from the bipartite graph, you are considering one vertex, that is u, and you are saying color used to that vertex u, okay? Color used is less than degree of the vertex. If there is a vertex u, okay, it's a bipartite graph, right? So here you will have like this. What they are saying is, the color used, okay, the color used is less colors you are using than the degree of the u. If here you are having 3 degrees, degree of this u is 3 means you are using less than 3 colors to color this graph, to color this, okay. You are using less than 3 colors to color this edges. Is that clear? That is what the meaning of this sentence. Any confusions? This is the bipartite graph. First thing you have to keep in your mind, and the next one is you are considering a vertex u and you are saying color used if this is the vertex u, and here you are having 3 edges that are passing through this vertex. Okay, imagine like that. If that's so, what you are taking is, if the degree here, the degree of this vertex is 3, right? The color you are using here to color these edges is less than 3. You are not using 3 colors, you are using less than 3 colors. That is how you are taking. Now, after this, you are going to use a lemma. Here you can see the statement of this lemma. This is the statement of this lemma, okay? Okay, listen. Here is also you are having a coloring and you are coloring the edges with the k colors, and that k color is an what? Be an optimal k edge coloring. I am explaining you that you the lemma's statement, okay? Don't get confusions. You have to write this inside the bracket. If this is till this what? This is the statement of the lemma. If there is a vertex u in G means, and colors, there are two colors I and J, such that I is not represented in this, to this vertex you are not coloring with the color I, and J is represented at least twice at U. Here you are using the color J at least 2 times. If you are having this vertex U, okay, you are not coloring with the vertex, coloring with the color I, they are saying, okay, I is not represented at U and J is represented at least twice. Color, you are coloring with the color J at least 2 times you are coloring at least, okay, it means 2 or more times you are coloring with the same color J. Then if that's so, then the component of graph of this, it means what? The edges you have colored with the color I, union edges you are colored with the color J. Okay, using that edges you are drawing a graph. That is graph of that contains U. In this graph you will have this vertex U. Okay, and this graph is an odd cycle. If these conditions are there, then this graph will have an odd cycle and this U present inside this graph. This is what the meaning that I come to know from this sentences, from this lemma. Okay, so here you are using this lemma in this proof. You can ask me why you are applying this lemma here. This might be the question. This is the question you have to ask to me, okay? Because I am thinking about why we are using this lemma here, why we are using this lemma here for a very long time, okay? Finally, I got an answer. So the answer is here. As I told you earlier, this is a bipartite graph, right? So bipartite graph means if this is a vertex, if here you are having 3 edges to this vertex U, right? In this every bipart you have to color the bipartite graph like this. If this is a vertex U, here are 3 edges that are incident in this vertex U, means you have to color with 3 colors. 1, 2, 3. You can't give same colors. Okay, here you are taking color of U less than D of U. It means from this what you will come to know is you are using the same color again and again. Okay, that is what you will come to know. If C of U less than D of U means in the bipartite graph, what you will come to know is you are using the same color again and again. You are using the same color, right? So okay, in a bipartite graph, if the degree of that graph is 3, then you have to use 3 different colors. That is what the condition in bipartite graph. Is that clear? So here you are taking color of U less than degree of U. So from this you will come to know that you are using the same color again and again. So that is why you are using this lemma here. This lemma is for using the same color. Using the same color in one vertex. Okay, if you are using the same color for okay, for one vertex, if you represent the same color at least twice at U, for one vertex if you are using the same color again and again, you will use this lemma. That is why in this theorem you are using this lemma. Is that clear? Okay, so finally I told you that why you are using this lemma here. I hope you understood because I explained again and again and again, right? Okay. Here U satisfies the hypothesis of this lemma, right? If this is happening, then this lemma is getting satisfied. U is satisfying this lemma, right? So that is what you are writing. By this lemma, you can write G contains an odd cycle. If these conditions are there, then graph of G of this is an odd cycle, right? So here our vertex u is satisfying that lemma, therefore that u is present in the graph G, our graph G, right? So here this G contains an odd cycle. So here this becomes the contradiction. To if G contains an odd cycle, then our graph cannot be a bipartite graph. So here you have a theorem. A graph is bipartite if it contains no cycle of G, no odd cycle. Okay, if there is a bipartite graph, then there is no odd cycles. But here you are getting an odd cycle. So what you are getting, the graph is not bipartite. That is what you are getting. Is that possible? Here in the first line you are taking G is bipartite graph, but now you are getting G is not bipartite. Is that possible? You are getting contradiction. Okay, so your assumption chi dash not equal to delta is wrong. So we get chi dash is equal to delta at the end. Thanks for listening.